PowerPoint?
Yeah.
Yes.
Yeah, you're good.
Okay, Okay, hello everyone, my name is Joshua Cho, and thank you for joining my presentation today. Today we will learn about logistic regression in machine learning. So please copy the link above. Please open Colab, please.
Can you send the link in Discord? So we don't have to
Okay,
use it?
yep,
Thank you.
Discord. Um, so I put it in the
I meant put the text in, so we could
yeah,
just click the link.
yeah, I'm trying. Just a second, please.
There we go. Very nice. Uh-oh. There's two M's. Hang on. Gotta remove that second O. There we go. Oh, this is cool.
But this allows a Python, and this is very nice a place for us to code. So we're gonna use Colab. All right. So now we're gonna watch a short video about logistic regression. I'm sorry, I'm not used to Discord, so can everyone see my YouTube?
Yes.
Okay.
I don't think it's sharing sound.
You can't see my YouTube?
I can see your YouTube. I can't hear the sound, though. There's no audio.
Can you hear it?
Nope. Did you share application sound? Are you sharing screen or application?
Yeah, you gotta share application and then hit share sound too.
Does anyone know how to share
You see
YouTube if
down
I
there
share
where
the
it
link?
says sharing screen, the green thing down there? On the all the way on the left side, there's a thing, the share screen button, right? When you click on the share screen button, there's an application window and a screen window. You have to click on the application rather than the screen. Which I think...
Yeah, I clicked the application window and then yeah.
Okay. In that case, you're one of the unlucky people who does not have the ability to share audio. And we'll have to have someone else share the video. Here, try one more time.
Alright, I'm really sorry, guys. I'll put the link. Could somebody play it for me? I'm really sorry, guys.
I'll make an attempt. It's okay. It's happened during my workshop as well.
Alright. So I'll put in the workshop text. Not again. I'm really sorry, guys. I don't know why this is happening.
Technical difficulties.
Make sure you put YouTube there. It says YouTube.
It'll work. I got it. Can just edit it. YouTube.com. Okay. Let's make an attempt. Close out some tabs real quick. Conference, paper, archive. Okay, this should work. Now, let's see if I can get this. Applications, logistic regression. All right, try joining me and seeing if this works. This is going to be interesting to say the least. All right. Can people hear that? Yeah or nay?
Yeah.
Yeah.
Okay, good. Good. All right. Is this at times 2? No, this is times 1 speed. All right. We ready, Josh?
Yeah.
All right.
Hey guys, and welcome to yet another fun and easy machine learning tutorial on logistic regression. To explain the concept of logistic regression, let's imagine that we want to classify whether a Pokemon will win a battle against another Pokemon. How would we classify this? Well, we could look at a set of features such as hit points, size of the Pokemon, attack rating, and defense rating. Now, intuitively, if your Pokemon has insanely high hit points, it would take ages for the opponent Pokemon to destroy yours, assuming the rest of the features are the same for both Pokemon. The same goes for size, attack, and defense of a Pokemon. So we can represent this using the equation below, where x is your features, b, also denoted as theta, are your coefficients. Now, if we just take two features such as hit points versus size of a Pokemon, we can use an algorithm such as linear regression and threshold the output. But what if we had an anomaly where the size of a Pokemon wins even though it has low hit points and is small in size? This would lead to misclassification. Also, another problem with linear regression is that it also gives values larger than 1 and less than 0. And this is where logistic regression comes in. Looking at the background of logistic regression. So, logistic regression is another technique borrowed by machine learning from the field of statistics. It is a go-to method for classification problems, despite the name logistic regression. It is not another algorithm for regression. Logistic regression is but similar to linear regression in a sense that they both have the same goal of estimating the values of parameters, coefficients. So, at the end of the training of the machine learning model, we got the function that best describes the relationship between the known input and the output values. Unlike linear regression, the prediction of the output is transformed using a non-linear function called the logistic function. Some variations of this name are called the sigmoid function as well as the logit function. The logistic function, also called the sigmoid function, was developed by a statistician to describe the properties of the population growth in an ecology rising quickly and maxing out at the carrying capacity of the environment. This is an S-shaped curve that can take any real valued number and map it into a value between 0 and 1, but never exactly at those limits, also known as asymptotes. Looking at the logistic regression equations, so the logistic regression hypothesis is defined as h theta of x, which is a function of g theta transpose x, where function g is the sigmoid function, which is defined as g of x equals 1 over 1 plus e to the power negative z. Okay, so back to our Pokemon example. If we take the hit points as x1 and the size of the Pokemon as x2 for now, we plot our data as shown over here, where x's show wins and zeros show losses. We can draw a clear line, also known as decision boundary, which separates the wins from the losses. From this, we can estimate or predict with high certainty whether a Pokemon with a certain size or hit point values will win or lose. You may note that the gradient is quite similar to linear regression gradient. The difference is actually because linear and logistic regressions have different definitions of h of x. So the nice thing about logistic regression is that it can be used to fit complex non-linear datasets, which means we can build more complex decision boundaries by fitting complex parameters by using higher order polynomials. So how do we go about finding the coefficients of the logistic function? Well, we can estimate the values of the coefficients using stochastic gradient descent. We'll learn a little bit more about gradient descent and stochastic gradient descent in a future lecture. This is a simple procedure that can be used by many algorithms in machine learning. It works by using the model to calculate a prediction for each instance in the training set and calculate the error for the prediction. We can apply stochastic gradient descent to the problem of finding the coefficients for the logistic regression model as follows. So given a training instance, number 1, calculate the prediction using the current values of the coefficients, and 2, calculate new coefficient values based on the error in the prediction. The process is repeated until the model is accurate enough. For example, the error drops to some desirable level, also referred to as minimizing the cost function, or for a fixed number of iterations. So you continue to update the model for the training instance and correcting errors until the model is accurate enough or cannot be made any more accurate. It is often a good idea to randomize the order of the training instance shown to the model to mix up the corrections made. By updating the model for each training pattern, we call this online learning. It is also possible to collect up all the changes to the model over the training instance and make up one large update. This variation is called batch learning. A little bit more on that in a later lecture. If you look at the applications of logistic regression, number 1 is image segmentation and categorization, 2, geographic image processing, 3, handwriting recognition, and 4, we can use it for healthcare, where we analyze a group of over 1 million people for myocardial infarction within a period of 10 years is an application of logistic regression. We can use for prediction whether a person is depressed or not, based on a bag of words from a corpus, seems to be conveniently solvable using logistic regression as well as support vector machines, or SVM. The reason logistic regression is widely used, despite the fact of state-of-the-art algorithms such as deep neural networks, is because logistic regression is very efficient and does not require too much computational resources, which makes it affordable to run on production. Yes, your server won't crash. If you look at logistic regression compared to decision tree, so both algorithms are really fast, and there isn't much to distinguish them in terms of runtime. Logistic regression, however, will work better if there's a single decision boundary, not necessarily parallel to the axis. Decision trees can be applied to situations where there's not just one underlying decision boundary, but many, and will work best if the class labels roughly lie in a hyper-rectangular regions. Logistic regressions is intrinsically simple, it is low variance, and so is less prone to overfitting. Decision trees can be scaled up to be very complex and are more liable to overfitting. Pruning is applied to avoid this. Okay, so that is it. Thank you for watching. Please don't forget to like, subscribe and share. Click that bell icon to get notified of more fun and easy machine learning algorithms. Also, animating these videos takes a lot of coffee, so I'll be really happy if you could support us on Patreon. Following lecture, we'll learn how to apply a simple logistic regression in Python. So see you in the next lecture. Thank you for watching.
Okay, thank you, James. So could everyone join my live screen, please?
We're in. It's very trippy. I like it.
Yeah. Um, so are you seeing my PowerPoint or?
No, we're seeing Discord.
Yeah.
Uh, okay. Are you seeing my PowerPoint?
Yes.
Yes.
Okay. Okay. So in today's workshop, we will make a model just one short class on logistic regression to make a binary classification, true or false. So our model will predict based on the given data characteristics whether the person has a cancer or not. So if 1, the person likely has a cancer, then X will represent the characteristics and Y will represent the binary value. So I couldn't find any useful images online. So from this slide, I had to draw or write, and they won't look great. So although the images that I made are not the best, I tried my best. So in our implementation, we will build a single layer neural network without the hidden layer. So we will have input directly into output, send it to activation function, and then have Y without any hidden layer between. So in order to explain, everything in this drawing will be implemented in our Python code. So before we write this into our Python code, I hope to explain why I why I got the equation. So I drew a single logistic regression model. We first have all the inputs, which are based on the characteristics with some unique weights, passed into a neuron, and the sum will have a value z, which will hold a value from negative infinity to positive infinity. So that is z value. So through the sigmoid function, we will represent this value as a probability ranging from 0 to 1. If a is greater than 1.5, because it's a probability, it will have a value of 1. If a is less than or equal to 0.5, then it will have a value of 0. In our implementation, if 1, then it'll mean true, and therefore the person will have the cancer and will use the data set already provided in the library. As you can see in my drawing, we say for pass when we say forward pass as we're going to the right. When going back to the left, we call it backpropagation because we're going back to update the values of W and B after first comparing A with the actual value and use partial derivative. To update the values of W and B, we are using partial derivative on L, A, and Z, and this makes backpropagation. The reason why we're using partial derivative is because we're trying to find the minimum value of W and B that will allow us to have the minimum resulting value from the lost function. The lost function for the logistic regression is, as you can see, is indicated as L. So minus y log A plus 1 minus y log 1 minus A. And that is the loss function. We're trying to find W and B that will make loss function to have the least value. So we will initially have random value for W and B, and after comparing our value A with the actual value, we're constantly backpropagating and updating the value. And once we found the partial derivative of L with respect to W and B, we subtract from the original because if it is positive, then it will make the value to decrease, and it will make the value positive if the value is negative. So the backpropagation allows us to constantly update the values of W and B, and if we use epochs to loop multiple times, we can make the result accurate. However, if we epoch too many times, that will make our program to literally memorize. So we should use a safe number of epochs. And for the epoch value, I'm gonna use 1000 for this program. So this picture shows a four-pass and using partial derivative in order to backpropagate. So from Z to A, got the number in terms of probability compared with actual value Y, and then backpropagate. So in order to update for L, I wrote the equation partial derivative partial derivative L respect to A respect to Z z respect to wi, L respect to a respect to z respective to b. And if we do all the calculation and subtract from the original, we will have the following equation. W times y minus a times 1, b plus y minus a times 1. And this is the code we're going to use for our Python code. And the process for getting this step will be shown in my next image. So this shows the steps for the partial derivative. Y, I got minus y minus a times 1 and minus y minus a times x. So before I mentioned how w is equal to w times y minus a times 1 and b is equal to b plus y minus a times 1. This demonstrates the process. So for L respective to a, we're holding all the other variables constant. So since derivative of logarithm a is 1 over a, we have this equation minus y 1 over a minus 1 minus y 1 over 1 minus a. For partial derivative a respective to z, it's pretty long. Once you follow my equation, you'll get a 1 minus a. And if you do z respective to w, you'll get xi simply, because we're holding all the other variable constant except for wi. So once you multiply all of them, as you can see below, you get minus y minus a times xi. And if you use the same values for partial derivative of L respective to b, you will get minus y minus a times 1. So we have finally found our values for w and b. So could you all go to our Colab? The link was on Discord. Could you all go to the Colab, please? Change windows, application window. Application window. Can everyone see my Colab?
Yes.
Okay. So at the top, you'll see plus code and plus text and copy to drive. Please click plus code, and you'll see a space in the middle. Okay, so I'm gonna start writing code. So type from sklearn.datasets import load breast cancer. Enter. Cancer is load breast cancer. So if you run it, unlike Eclipse or any other thing, Colab allows us to run a single line by single line, and that is why I like Colab a lot. So, oh boy, from sklearn.datasets, import load, LOAD. So from sklearn.datasets, we're calling load breast cancer function, and that will give us the cancer value. and then click plus code again. Type print cancer.data.shape, cancer.target.shape. So data has two attributes. No, not the data. So cancer has two attributes, data and target. And each has an attribute called shape, and shape allows us to see the dimension. So they're a matrix. So data is 569 times 30 matrix, and target is 569 times 1 matrix. So data is going to be X, target is going to be Y. So if you drag your mouse a little bit below, you'll see plus code, like this. Click again, and we're going to write more. X is cancer.data, Y is cancer.target. Okay, so from sklearn.model.selection, import train test split x train x test y train y test train test. And train test split is a function from the SK model selection. Split x y stratify y test size 0.2 random state. And the random state can be any constant number. But the stratify y and test size 0.2 means we're gonna split x and y, and y is gonna have 20% of all the 20%. X will have 80%, so we're dividing. So yeah, X train and Y train will have 80% of all. X test and Y test is gonna have 20% of all. So we're having training set, the testing set.
Josh, can you just like
So
show the whole bottom line right that you're on right now? Just like zoom over
what should I do?
to show the rest of the line, like the line of code. Just can you move the Yeah, that works. That's fair. All right, let's check. That's actually better.
Right, thanks.
Yeah, no problem. Just so we can get it down.
So we're gonna print what they look like. So x train.shape, y train.shape. Print x test.shape, y test.shape. And when we print the result, this is gonna show how training set has 80% of all the sets, and testing set will have 20%. And you'll see from the result. So you can see how like 455 and 114 is divided into 80% and 20% sets. So X train is 455-30 times 30 matrix. Y train is 455 times 1 matrix. And all the values within Y train is either 0 or 1, as I showed in the picture before. And we're going to add it more code. So, and now we're going to write a short class. So this is going to be a class. Import numpy as np. And numpy is a very useful especially in Python, and especially in machine learning, it's sort of like a matrix, an array, and this has many useful array methods. So class logistic neuron. So this is a Python init self self.w is none, self.b is none. And remember the w and the b value that I showed in my picture? That is the w and the b value here. And w is the weight. Define forpass. And forpass is a function name or acronym that I made for the forward pass. Self x z np.sum x times self w plus self b. Remember how at the very left we had a neuron of adding all the xw values and adding b at the end? That's showing the forepass. We're having z first. And return z. Define backpropagation. Self x error. And error is the result after comparing a with y value, the binary. W grad represents W gradient. X times error, B grad 1 times error. Return W grad B grad. And the gradient value, the reason why we're multiplying x times error and 1 times error was I demonstrated using the partial derivative. But if you would like, I can go back to the image before. If anyone hopes to look at my partial derivative equation again to check. So define activation. So activation function, this was part of the four-pass process. It was one of the neuron. So it uses a sigmoid function and then makes a value into to range between 0 and 1. Self z. A is 1 plus, and this is why NumPy is very useful here. Return A. Define fit self xy epochs 100. So we're gonna loop 100 times. But if many will think epoching many times will always bring it the best result. Like if I set epochs to be like 1 trillion or 1,000 trillion, many people might think it'll bring a good result, but actually that will make our program to literally memorize all the data sets. So we can't have a too large value. But self.w is we're initializing the w values, mp1s, shape 1. So if X is 10 by 10 matrix, then W will have 10 by 1 matrix. And the dot shape function is setting all its elements. No, we're getting X coordinate of X matrix. And self B as 0. For I in array epochs, we're looping for xi, yi in zip xy, and the zip function allows us to retrieve x and y one by one, because here the matrix, like we said how it is 455 times 30 matrix in the 455, we're getting one by one. Z is self.forepass, xi. A is self.activation.
Josh, 1 second.
There.
For that for loop, 4x underscore I, y underscore I, did you mean to put zip there?
Yeah, I put zip. Is there an error?
No, I was just wondering because it keeps autofilling for me with zip, so I was just making sure.
Oh, zip xy. Zip
There
xy.
you go. All right.
Thanks, Matthew.
Yeah, no problem.
Error. So error is gonna be y I minus a. And if anyone wants, I can always go back to the picture, like my partial derivative equation, why all these equations are written just like this. So please feel free to stop me at any time. W gradient, B gradient is self the back propagation x I air. So we're sending xi in the air at the back propagation we're updating. W grad and self of W, we're subtracting W gradient, self dot B. And the reason why we're subtracting is to find the minimal value for W and B for the loss function. Okay. Define self x. So z is equal to self dot forepass xi for xi in x. So predict function will allow us to predict based on the characteristics we have. Self dot activation and p dot array z. Turn a. So this is gonna be 1 if it's greater than 0.5. So if we run, I guess I don't have any errors, so let me check again.
I know for a fact you
None.
have an error on the activation function. You return
Yeah.
ABS instead of A. I
That
called that
Oh.
earlier.
Hey, thanks for the catch. Let me check again. Send p p return z. It's 1 plus send pxp. So yeah, so I think I'm all set here. So we're gonna continue more writing. So we're gonna make an object of logistic neuron. Make some mistakes because it's morning time here. So I might make some mistakes. Neuron, logistic neuron, neuron.fit, train, y train. Remember, we're training the neuron. We're not using the testing set. We're using the training set. So if we run, so yeah, it looks good. Disregard the overflow, runtime running. Neuron.predict, x test. Now we're going to use a testing set. Oh, we got the result now. So remember, x test was 114 by 30 and 114. So based on all the x's, based on the characteristics, we found we predicted all the values. So this is for the all 114 of them. 114 examples with 30 characteristics. We predicted the first person to have false, so no cancer, second to have cancer, third person to have a cancer. And this is our prediction. This doesn't mean we are correct. So we're going to compare our result with the actual result. So by test, let's see, false is true. We can see how they're very close. And we're going to calculate how close they are mathematically. So np.mean, you want to predict x test y test. Yeah, so we're 82% correct, and that is pretty good for our result. So we have 82% correctness for our logistic neuron. So this simple short class brings us to have 82% correctness. And that is pretty good, just for on this
Josh,
code.
can you go back to your activation method there? I don't think I copied that right.
Yeah, I'm getting an
Oh, can
error
you
in
see
my
it?
activation as well. I'm
Yeah.
getting that it's for some reason my z is none. I'm trying to figure out why.
So it's exponent negative z. I'll try to run that.
Somewhere where I'm passing in, it's not doing it right.
Yeah,
What
I'm
have I
getting
done
an
wrong?
object is not callable in activation, and I don't know why I'm getting that.
So that's probably a minor spelling error in your code. It's probably the spelling error.
Yeah, I mean, I thought that might be, but it's really like spot on.
Did you put z equals self or pass x I?
Let me see. I'm looking at activation. So, well, let me see if I possibly made an error. W grad, B grad, activation. 1 divided by, 1 plus. Oh, wait, maybe that's it. 1 divided by, maybe. Let me see if that does anything. I don't think so. No. Logistic neuron object has no attribute backdrop. Wait, did I not call it as a, what line is that? 29. Do they have line numbers on here? Other than
Where are you having an error?
I think I probably just screwed up somewhere. It says line 29 on mine. But,
Here, Matt,
do you
share your screen.
yeah.
I just figured out what was wrong with mine. I forgot to return z from the forepass.
Oh, that could be.
I mean, do you want me to copy and paste the code to our Discord?
Yeah, sure.
I mean,
I probably just called something like it says right here the error is logistic neuron object has no attribute backdrop, so I probably called the backdrop method as
That's
just like an
called
attribute.
backprop, not backdrop.
Oh,
You call it as backdrop down in
backdrop.
your fit method, but it's actually called backprop,
Wait, so
and you
oh,
call
you
it as
got it?
backdrop
where did
down
I
in right there. Your mouse is like basically on
Oh
it.
my goodness. How foolish of me. Alright, let me see. Does that fix it?
Yo,
Yeah, let's
all
fix
right,
it.
clean.
Alright, cool. Thank you.
Nice.
And then adding just neuron.predict x test.
Yeah, I have to add that.
Cool.
Give me a second.
This is a lot like Jupyter notebooks.
Oh yeah, Jupyter.
It really is Jupyter
Yeah,
Notebook.
Jupyter.
Yeah, I mean, yeah. I wanted to say
So Matthew, were you able to fix for now?
Yeah, I was, yeah. I'm running
So
now.
yeah, so just one more. Could everyone join my live screen, please?
Yeah, I think everyone's in it.
Okay, so application window, your entire. So is everyone seeing two screens, one Colab and one PowerPoint.
Yeah, you're good. I mean, they're
We're
both
seeing two screens, right?
yeah, it's like split screen.
Yeah, you get the
Right.
code on one and
Nice.
the PowerPoint on the other.
Nice. So the reason why all the code is explained in my drawing. So I put Z is sum of all x and w plus b. At the left, plus neuron, the first neuron adds all the characteristics with some weight, and we're adding b. And then this brings z, which has a value from negative infinity to infinity. We pass it to a sigmoid function, and that makes it into a. And that is exactly the activation function. We're setting z, and once we pass into 1 over 1, 1 over 1 plus e over 1 minus z, that brings a, which is between 0 to 1. That's the probability. And we compare with y value, which is the error, ERR. And then we are, and I explained at the bottom, you can see how the partial derivative, we got the equation. All the steps here, I indicated that wi is equal to wi times y minus a times 1. No, actually, there should be plus between b plus y minus a times 1. That is exactly in here. Self times w minus w gradient, self times b minus b gradient. The gradient is found in the backpropagation. And the reason why we're doing x times error and 1 times error is because of the partial derivative we got the equation from. So 1 minus a is the error times x. 1 minus a is the error times 1. And that is exactly implemented in our code. So do you guys have any questions?
So we used one single neuron. This entire network was just one neuron, right? There was the input layer, which was technically, you don't technically count the input layer as multiple neurons. So we literally just had one neuron with a weight on each of the incoming inputs. And then there was just one bias number, is what I'm getting out of this.
So we're
Right?
using multiple neurons, but this is a single layer.
Explain
Yeah,
how we're
so
using multiple neurons. Because those input neurons aren't actually neurons. We're not counting those input neurons as neurons.
yeah, so disregarding the input, the output, we have the activation function and the threshold function
Are you
between.
counting the activation and threshold as separate neurons?
Yeah, I mean,
Okay,
you're
that's fine.
getting
That's
different
legal.
results. We're
Normally,
getting the different results here.
yeah, normally I would consider all of them as the same thing, but I can see why you could consider them as separate things. I mean, people have special ReLU layers and stuff in their networks, so and sigmoid layers and such. So it makes sense that you can consider them their own neurons.
Yeah, in order to explain, I feel like separating them is the best way for me to
I think
explain.
so. It's a lot easier than
Yeah.
explaining the sigmoid neurons as a single entity.
Yeah, on Google, they don't really have any useful images. That's why I tried to draw. They didn't have this kind of image.
Right,
So
right.
that's
Yeah.
why I drew. Yeah.
I think this is a good example because it lets you really see the fact that your 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 activation is a separate thing and you're passing the summation into the sigmoid. I think that that's valuable.
Yeah, and it's fascinating how the partial derivative allows us to find the values, and we can use the values in our Python.
Yeah, it's very neat.
So I don't want to be that guy to ask about the math, but what about the math a little bit? I don't know. I feel like you did a lot of math, obviously, on your paper there. So you started out with those two partial derivatives, it looks like, and then you pretty much worked out the loss function from there.
Yeah, so you see the arrow at the top, like how it's overarching over sigmoid function, the leftmost neuron? Like, can you see red circles that I indicated at the top?
Yeah.
So, um, after passing to sigmoid function, we have a value as the probability, and we are comparing its value with y, then that's the error. And um, um, okay, so we're trying to find the partial derivative of L respective to W and partial derivative of L respective to B. And the reason why we're using derivative is because by holding all the other variables constant, we're trying to find value W that will make loss function to have the minimal value, and B value that will make the loss function to have the minimum value. In order to do so, you have to do step one by one backward. And that is why in order to do partial derivative of L respective to W, you start with L respective to A, then A respective to Z, and Z respective to WI. We have to go backward. And that is what we call backpropagation.
Yeah, that's just
And
taking advantage of the way the chain rule kind of works there with the
yeah,
Laplace.
yeah, and subtracting allows us to update. And that allows us to find the minimal value for the W and B for the loss function. And the loss function for the linear regression is different. It's a square root of the differences. The loss function for the logistic regression is this one, y log a plus 1 minus y log 1 minus a.
Okay, yeah, it's good to get a little bit more of a concrete explanation. Thanks.
Yeah, thanks, Matthew.
No problem.
Anyone else have a question? If no one has a question, we can end for this meeting, today's workshop. So thank you everyone for joining my workshop, and have a good night.
Thank you, Josh. That was a great
Thanks,
workshop.
Josh.
Before
Thank you.
everyone yeets, let's go over the schedule for the week really quick. So, again, Josh, thank you. That was a great workshop. As someone who works with machine learning on a daily basis, that was a really good introduction. I think that it's valuable
Thanks.
to understand what basic machine learning does before you do stuff like jumping into TensorFlow. And I think that that's definitely, I think that maybe in the future, a good workshop would be then to take this over to a machine learning framework, which automatically calculates the gradient for you, which is actually really nice because for everyone who the calculus scared, it's nice to know that modern machine learning frameworks do the calculus for you behind the scenes. So you don't actually have to do any math at all, and it handles that for you. Which was very appealing to me the first time I saw TensorFlow. I was like, oh my god, I don't have to implement backpropagation manually. They do that for you as long as your loss function is, what do they call it? Differentiable. As long as you have a differentiable loss function, TensorFlow will do the math for you, and it will do it numerically. So you don't even have to worry about any of the gradient calculations, and it's really nice. But beyond that, all right. So if the schedule for the rest of this week, tomorrow, Matt Keelan is going to be giving a workshop. Matt, would you like to speak about what your workshop is on briefly?
Yes, thank you, James. I'm gonna be giving tomorrow at 8 o'clock in this Discord server a workshop on software design patterns, and what we're gonna really do is honestly, it's gonna serve more as an introduction and talk about a few of them. and why you'd want to use them. And then I'm going to give some examples of like common software design patterns you probably see like, in certain software to do some things. So I feel like software design patterns are specifically one of those things that people don't really know that much, at least at the undergrad level. Or if they learn about it, they don't learn about it that much.
Thank you, Matt. Yeah, it's going to be an exciting... Software design is something that really doesn't get enough credit at this school. Like, the closest class that comes to teaching good software design practices is probably 418, but 418 is really bad. At least it was when I took it, and doesn't give a really good overview. So I'm really happy that Matt Keelan is going to be going over that tomorrow. It's going to be a great workshop. On top of that, on Friday, we're having side project development night. And then next week, Monday night, we're going to be having professional development night. And in terms of election related news, tomorrow night at midnight is the last day to declare candidacy for eBoard. If not enough people run for positions, or if no one's first position conflicts, people will just end up winning by default, and there won't be an election. On top of that, there is... Let's see. I think we're going to... The election committee was having a debate on whether to open up the attendance so more people can run, since no one's running, and Tony provided us a new metric. And we never actually finalized our debate about that. We were kind of split down the middle. But there was essentially... I think at this point, it's probably a good idea to open it up a bit more, because at this rate, only one person has announced so far, and there's only one day left to declare. So we're probably going to make it easier to... We're probably going to make it easier to run. For those of you who are interested, we might extend the election deadline a bit if that happens, because it would make it more fair to have that go out a bit farther. Beyond that, there's really... so assuming not enough positions do end up getting filled and no one runs for secretary, treasurer, or any of those, in that case, we will probably just ask for people to fill them, and it will be on a first come, first serve basis. And if you are upset by that, you should run for the position rather than risking it on the first come, first serve asking basis. So I think that's what we're going to do. Otherwise, if we do get enough people for all of the positions, elections will be held starting on Friday into Saturday. So that's what's happening in IEEE eBoard election-related news. If you have any questions, you can DM me or anyone on the election committee. I think that's about it. Are the t-shirts free? Yes, Carter. The t-shirts are free for the members with the top 30 attendance. Anyone who's in the top 30 attendance is guaranteed a t-shirt of your choice and size. Please contact Matthew.
Oh, no. I'm finalizing this. I got all you guys. Great.
Who's finalizing it right now.
I'm doing it right now. Robin.
So, if you want
what do you want? Which shirt?
Oh, what do I want with a shirt?
Yeah, which shirt? Which shirt?
What left?
No, not size. Just whatever. Do you want the meme one with face on it?
I will get the leftover.
There is no leftover. We're custom ordering.
Yeah, I have to.
Oh, really? Oh, okay.
Yeah.
So which one do you want?
I get the... Wait. The UAlbany logo one.
Okay. All right, that's everyone. No one DM me. I'm all done. Goodbye, everyone.
Okay. We're also ordering some extras. So
yes, we will have.
If you haven't contacted Matt with a vote and a size, do that like literally right now.
Yeah, I'm about to send this to Josh and walk my dog. So if you want to put something in, do it now.
Wait,
yes.
The one that we put in announcements, that's the one that, like, if you voted on that, are you good?
Yes.
You're good because you voted on which shirt you wanted and which size. But some guys voted for the size and not which shirt, which leaves me with nothing to work with. So okay, yeah, you're good. You're good, Matt. But okay, yeah. So I'm finalizing this and I'm sending it to Josh. So anyone that wants to change their pick, you have to DM me like right now.
I see there's also some people in the main chat. I think you. Oh, you saw those, right?
Yeah, I
Okay.
pinged the people I
Okay.
need to. All right. So Robin wants the UA one. Okay, great. Thank you.
So with that, thank you for coming, everyone. I hope to see you at some of our events later this week. I strongly encourage those of you who are able to run for e-board positions to run for e-board positions. If not, I strongly encourage those of you who were not allowed to run for e-board positions. We might open that up to attempt to run for e-board positions. We will see. So with that, thank you for coming, everyone. Have a nice night. Bye-bye.
Good night, guys.
Good night.
Okay.